Hello, I am Gabriele Scannicchio, a biomedical engineering student at the University of Kent. Today I have prepared a presentation about the applications of the principles of mechanics of materials in biomechanics. Specifically, I'm going to talk about the loading effects on bones. The article Flexion of the Elbow, an excerpt from Introductory Biomechanics from Cells to Organisms by Ethier and Simmons, was used as a reference for this presentation. Here, an experimental model for the internal effects of loading on the radius and ulna, the forearm bones, was presented and discussed. The bones, for the purposes of this model, are considered one single unit and are modeled with a free body diagram. Generally, when tackling these problems, the most commonly used model is the Euler-Bernoulli beam. This is a beam with a symmetrical rectangular cross-section of constant length, height and width across all the planes of the Cartesian coordinate system. When solving a mechanics problem, the first thing to do is to determine what is the body or surface of interest. This is known also as a control surface. In this case, as we've implied earlier, the control surface is going to be, of course, the block formed by the radius and the ulna. After this, we need to highlight all the forces acting on the control surface in order to determine whether this is moving or not. The key forces in this model, of course, are exerted by the muscles. Specifically, they come from the biceps, brachioradialis, and ECRL. All of these exert forces at a different magnitude, applied at different angles with the control surface, which are shown in a free body diagram, which can be constructed with this information. However, despite the muscles being commonly viewed as a single unit, in reality they are composed of thousands of small fibers. These fibers contract upon nervous stimulation, and each of them exerts an infinitesimally small force that can be added together with other forces exerted by other fibers. This, of course, results in the net force that we see applied on the load. Therefore, we can say that the load here is distributed, that each fiber exerts its infinitesimally small force to react to an equally infinitesimally small part of the load's mass, the loading object's mass. This, of course, means that the load must be treated as a distributed load. In these cases, a distributed load can be changed to a concentrated load using knowledge of the pattern that the forces distribute along. In this case, the pattern in question is the physiological cross-sectional area, or PCSA. We know that each force exerted by the muscle depends upon the amount of surface, the width of the surface that it reacts to, and the net magnitude of the force itself. We can apply the N multiplication rule to determine the equivalent concentrated load that the muscles must react to. After this, we can draw our free body diagram. And we can begin applying the principles of mechanics. Of course, like I said earlier, we can reasonably assume that the body is not moving. This, of course, would entail all the forces acting on it being in equilibrium, that is, their summation is equal to 0. After calculating after calculating all the forces required, calculating the forces required for the body to not be moving requires knowledge of the torques generated by those forces. Those must also be in equilibrium so as to avoid the body rotating. Again, the summation of all torques must be equal to 0. At a microscopic level, however, even if the body is in equilibrium, any force applied onto it will result in a reaction by the molecules that make up the matter it's comprised of, to prevent them from being displaced too far away from their initial position due to inertia. We can study the effects of these internal forces by simply cutting the body along a certain plane and studying it section by section. Of course, this is the method. This is known as the method of sections. When the force acts on the body, it distributes along the surface it acts on, which describes the pressure. This reaction force, the reaction force exerted by the molecules, acts on the same surface on which the force is exerted. It's for the simple purpose that there is where the molecules are displaced more. In doing so, of course, the reaction force generates an equal and opposite pressure. This is known as the body stress. Even though the loading force and the reaction force must cancel out, otherwise the body would break, their interaction forms a couple to generate a torque. This torque, of course, describes an angular displacement, which is what causes the body to bend when acted on by a load. This is known as the bending moment. However, when the body bends as a result of bending moments, again the molecules that make up all its matter will try to return to their initial position. This is simply a result of inertia. This is simply a result of inertia. When the trajectory of the body's displacement, however, is curvilinear, then the mass will not be the only parameter involved in the equation. Instead, the curvation of the trajectory will also be responsible. This describes the moment of inertia of the body. In the context of mechanics of materials, the moment of inertia, the resistance that the exerts to being displaced, along an angular trajectory, is known as the second moment of area. This is dependent on the body's geometry. It is known that every body undergoing bending will change its length as a result of the molecules exerting their reaction force. However, alongside the body's center of mass, where of course the most resistance can be expected, the body's length will not change. The axis that passes through the center of mass is therefore referred to as the neutral axis. We know that the stress exerted on the body depends on the bending moment, the distance from the neutral axis, and is also reduced by the second moment of area. We can apply the n multiplication rule to say that the stress equals the bending moment, the distance of the point on which the external force is applied to the neutral axis, divided by the second moment of area. However, this is not sufficient, as like we said earlier, the reaction force applied by the body to remain in its current position also distributes along the same surface area as the external force, meaning that we need to add that to the stress, to the body stress. Now, we can consider the unit formed by the radius and the ulna to be as a hollow tube, and we can apply the method of section to calculate the bending moment for the different portions of bone acted on by the forces exerted by different muscles. We can plot a graph of the bending moment for each section acted on by a different force, and we see that in different sections the bending moment's magnitude increases linearly. This, however, raises a key question, because normally in an Euler-Bernoulli beam the bending moment is expected to increase parabolically. We can explain this by our use of a distributed load, of a concentrated load, as opposed to a distributed load, which is what is most commonly used. This was done for simplicity's sake. However, when the load is distributed, the energy required to produce the same effects increases parabolically with the distance from the point of application of the force. Of course, this is simply a result of the inverse square law being at play here. We must also consider the fact that there is only one support responsible for all the reaction forces, responsible for maintaining the body in its initial shape, in its initial position. Of course, this means that the model used by the article is not an accurate representation of what happens in the forearm bones. It is, however, it can still be considered. It can still be used by taking the necessary approximations. We must also consider that the radius and ulna have multiple contact points. These are made of different materials whose stiffnesses are prone to variations, because as bones rarely connect directly. This would normally because if they did connect directly, then they would wear down very quickly as a result of the immense frictional forces generated. Instead, between bones there are different layers of connective tissue which make up layers of interosseous membrane, and interosseous membrane is known to have effects on the distribution of the load. We must also consider the geometry of the contact surfaces, which are irregular and are again prone to variation. This would further complicate applications of the method of sections, making an accurate depiction of the loading effect on the forearm very complicated.